And while we're going through, I will ask the people to mute yourself. And if you have any question, you can unmute yourself and ask the question at any time. Okay? So again, I assume you have all the materials I sent to you, and we'll directly, I'm going to share the screen. So for the last two parts we talk about in the ImageJ, what we want is when you have an image, we notice that the part your interest, which is the signal, and you want to distinguish this part from the background. Okay? And once, if you can do a nicely job on this, you can achieve something we call the mask or the binary image, which in this image, all the pixels are divided into two groups. One is the white pixels, which is the signal, our object, or what we call our region of interest. And the other pixels, which are black, those are the background pixels, which we're not interested. But once you can achieve such a good, nice mask image, we can use a function that is probably one of the most used functions in the ImageJ, especially if you're doing the cell counting. That would be the analyze particles. You can use that one to automatically gain you the outline, the ROI, for all the white objects in the field of view. And inside that function, you have a lot of kind of factors, the parameters you can choose to allow you to choose only objects with a certain size, with a certain shape, it's on the edge or not. And once you achieve those ROIs in a list, then you can apply those ROIs to your raw image. You can do the corresponding the measurement. And so today what we're doing is that sometimes your image, it may not be your raw image, may not be very good. So if you directly go to a thresholding to use the intensity to separate the pixels into two groups, which is one part is a white pixels, that's your signal, your object. The other part is just the background. If you directly set a single thresholding value, it may not work. So you want to do something before you actually do the thresholding. So we will introduce some basic ImageJ functions on how to whatever called the pre-process your image before we go through the thresholding. So if I have the material, we'll go to the folder A, smooth filters. So if you open this, I will open the cell. So this is, I would say, a fluorescence image of the cell. To make it, I think I can make it clearly. I will say file, the lookup table. As you can see, this is an image. We can kind of clearly see those are the cell, I will say. Our goal is still the same. We want to ask the system to automatically identify the cells inside this field of view. We want to count how many cells, and we also count the size of each cell and the mean intensity, total intensity of each cell. So when I look at it, you will notice that this is kind of a, let's say, noisy image. As this part will show this is the background, but you can still see some pixels that are showing up. It's just the image is noisy, just by chance, some are noisy, some pixels showing up a strong signal. So now if we see we did in the last week, I want to automatically use the thresholding to mask the image. So I will say a background kind of low intensity, our signal is high intensity. So I go to the image, adjust threshold holding. I'm going to play around with this. So if I try to set up kind of a thresholding, I think it get a hold of all these cells. Then we realize we began to have a lot of those single pixels showing up. Those are the pixels in the background. They supposed to be has no intensity, shouldn't showing up here. But because the image is noisy, that by chance many of them actually showing up an intensity higher than the thresholding we set. If we want to get rid of all the noisy ones, then we don't have those noisy pixels showing up. But then all the cells, we do not have a very nice the mask for the cell. So here is the image. What our problem is the image is kind of noisy. So we cannot just simply apply a thresholding. Okay? Something like this, you click apply. Let's see. I just need to, I think it's always, we need to set up something. Once you apply, you will see this kind of quite, all those dots, it should not be the cell, but it does show up. We do know from the analyzed particles, you may set up some kind of size limit to get rid of the smaller one. But sometimes in reality, those ones get connected to your cell, right? That you don't like it. So we want to do something before we actually using the thresholding to make it less noisy. And to do this, I will say the best way, or what is the right way to do this is when you take the picture, you change your acquisition parameters to make it a better picture. You're using the cameras, you're choosing a longer time, longer exposure time. You're using a confocal, the scanning confocal. You take a more average. You turn on the laser power more, turn down the gain to make the noise less. So the ultimate way to solve this problem is to get a better image to analyze. Okay? We can do something on the digital image analysis set once we already have the image. But all we did it here, we use the smooth filters. We'll just do it in a second. It has some disadvantage to it. We sacrifice something to it. So the best way to solve your digital image analysis problem is always get the best raw image you can. Then you begin to do your analysis. It saves a lot of time. Okay? So in this case, if you realize this is my data, when we begin to analyze this data, my data is too noisy. Your goal is you should go back to the microscope side. When you take the picture, we try to make the raw image less noisy. Then we can directly use the thresholding to apply it. That makes your data analysis much more reliable. Okay? But now let's say we already taken an image. Those are the image like I take it 2 months ago. The slide is already gone. Okay? So what can I do now? So here is we can use something. We will smooth the image. We'll make it less noisy. All we did is we basically do some calculations on the image with this labeling image. So to make this one more clear, I will use the image lookup table file. So to smooth this image out, you normally have 3 options. That will be in the process filters. You can do a Gaussian blur, you can do a median filter, you can do a mean filter. So let's say if you try the mean filter one. Once you click on it, it asks you to introduce in one parameter, which is the radius. This radius depends on how many neighbors you want to use to smooth the signal. Let's say I go to 1, and I can click a preview to see what it looks like. You'll see now it seems much less noisy, because if you use 1, that every single pixel in the 2D image, it has 8 neighbors. Getting? And it takes, including itself, is a 3 times 3, the box. All the 9 pixels, they add it up, they divide by 9, and they use this one to replace your pixel intensity. Then you apply this one to all the pixels. If you put the radius at 2, they will take more pixels into it. You can say once you go to 5, it's getting more, the data getting more smoother and smoother, less noisy. But you can also see the image get blurry. Once I get into, let's say, 20, you basically lost your signal. All the cells kind of blended into the background. So all those, the mean, median, the Gaussian blur filters, it use your pixel combined with the neighboring pixels, then take either average, mean, or some like a Gaussian blend to make it smoother. So you get a smoother image. Your image won't be that noisy, but you lose your resolution. You make the image blurry. Okay? If you do the image on the acquisition side, you take a longer exposure time, you take more average to get your image. You have the same quality of the image, but you do not sacrifice your resolution. You still have a pretty sharp edge of the cell, not like here if you use 4. You can see those three edge become quite blurry. So this is not the best way to solve the problem. We can do it in this way, but again, I also want to emphasize this. Once you have your raw image, you do the image analysis, you found some kind of problem, some kind of disadvantage at your image, your best way is to go back to the microscope, get the best raw image you can, then you start your analysis. So now let's say, I will say in this case, I will just use 1. And then I'm going to do the thresholding. So now you can see this looks much better. Compare with the before, this is a raw image. Then I go through the threshold holding. You can say much. The left one is we only did one function. That's a mean filter with a radius choose of 1. This is process filters. I use the mean filter and with the radius as 1. The same thing, here's our raw data. We can also try a different one. Let's say filter, we call the median. 1. And then when I play around with this, it's also maybe not as good as mean, but I think it also works fine. And you can also try, and let's say, open the raw data again. And I'll try the Gaussian blur. Maybe also 1. Maybe this time we'll try 2. Get it? And play around with this. Maybe 2 is too much. I think the blur is too much. Probably, let's see if we can go back. I will only do the Gaussian blur 1. Then I play around with the thresholding. So if I combine all this together, this one I use the mean filter, radius 1. This is a median filter, radius 1. This is a Gaussian blur filter with the radius of 1 pixel. So your goal is go through your data, try to say what smoothing filters works the best and what radius choice works the best. It's a mean filter, radius 2 pixel, 1 pixel, I think. In this case, I will just use this one. I think the mean filter radius 1 works fine. I just apply it. And do the same thing as I did before. In last week, I fill the hole. And once I get a good mask image, I can do a water shading, separate all those cells, and I go through the analyze particles. I'll say my cell should at least like 10 pixels. I don't want to cell on the edge. I do want it to get all the white object, add to the ROI manager. I click OK. And then I open the raw data. This is our selection. So I will say, it depends on personal choice. I'm quite happy with this. I think that I know my raw data is not specifically very good data, getting, and I don't actually do much. I only go through a main filter with the radius as 1. Then I feel I get a quite good selection on all those things, except for maybe this one. This I think is one cell, but somehow here it gives me the watershed cut it off. Okay. You can try if you use the median and or Gaussian blur, if this can give you as one. But for me, I would say generally, I think for this data, I'm fine with it. We have total of 70 cells. Getting maybe one of them I get it should be one, I cut into two, and apply to another image, maybe it should be two, but we consider it one. Getting? I think that's within the error range. I will just take it. If you don't like it, you can try to see if you manage through all the different filters. Then you go to the thresholding. That may give you a better result. But again, our goal is to try to set up a protocol so we can use the same protocol on all the images. Like here, I can play with it, min filter, radius 1, or I can use the Gaussian blur, the radius 1, 2. But once I fix it, I will want to use the same protocol on all the images. So all the images, what we need to do is I open the image, I go to the min filter, radius 1 applied. Then I go to the thresholding. I either set up some like a value directly, or I use some algorithm to do it. Then I apply it, get a mask image. I use the image process binary, fill the holes, then process binary watershed, separating connecting cells. Then I go to the analyze particles. Okay? So it's always try to incorporate those smoothing steps into your protocol. Always make sure you use the same protocol to apply to all the images. That makes your analysis consistent and reliable. And there's another data here. It's a chessboard. You can follow with the PDF file I attached that for the slide. This is just a reason, a kind of example to show. Most of the time, I feel my personal preference is I would rather use the median filter than the min filter, because the median filter keeps the edge better than the min filter. The min filter kind of blurry the edge too much. So especially if you want to identify the cells, the cells kind of small, that the median filter may give you the result which makes a better representation of the cells. So this is about the smooth filter. Any questions? So if not, we're going to go to the next part. That's the part B. This is another kind of image problem you probably encountered. So let's open this cell image. So this image goes to the file lookup table to show it better. It's not only noisy, it actually has another problem. So now let's see if I can see this part is kind of noisy. So I will say I do some smoothing. Filters, I'll take a medium. I smooth it a little bit. And now I want to identify the cells. So I do the thresholding. Now when you move the thresholding value, you begin to see if I set up a value which on the right side we kind of get a nice overall the size, the area of the cell, then on the left side it's kind of all thresholded. Okay? We do not get any cell in the left side, but if we increase the thresholding, when we get a nice cell outline, kind of the area on the left side, but on the right side, we began to lose it. This cell, we totally lost it. Okay? So the problem for this one is, this is not an evenly illuminated image. The left side is has a higher intensity on the right side. So if I draw a line, and let's say I want to show the profile along this line, we go to Analyze, Plot Profile. This part is probably the cell we go through, but here we mostly go through the background. You will see the background continuous goes down. From out here is like 100, goes down to like 20. It's unlikely this is actually from the sample. It's most likely that you have a problem on your illumination on the microscope. It's just the way you put the light, the excitation light on the sample. The left side has much stronger light on the right side. So it's actually not very uncommon, really. People say it a lot. All the microscope, you need continuous kind of tuning up, kind of the alignment. No system can be perfect for a very long time. So when this happens, okay, again, if you want to solve this problem, you have to always go back to the microscope and realign your microscope. Okay? That's basically the only way you can do it. You know you have a problem on your microscope. That shows very clearly on this image. If you want this project to keep going on, you have to solve this problem. But again, now let's say in a less ideal reality, the image is already taken. Those are the live cell image. The cell is long gone. I take it last month. Then I just realize this problem. Can I still kind of use this data? Yeah, probably you can. We can try to solve it. But just keep in mind, this is not the ideal case. You should go back to your microscope. Make sure the raw data coming here is good, right data. So now let's say if I already have the data, how can I kind of correct it? So basically in this case, we were assuming that the left side has a higher background value. Okay? So we want to compensate on this. Okay? There's two ways. Here we will use the local background subtraction. Later on in the example in the image calculators, we will use the reference image to correct it. The later one is a better way to deal with it. But here we can just show you, in this case, use this as an example to show you the local background subtraction. So our goal is to say, we look at this image, if we consider the left side as a higher background on the right side. So we want to first cut off the background, then I do the stretch coding. But we cannot use a single background value to apply to all of them, because this part has a higher background than this part. So I want the program, when they cut off the background, they do a calculation to actually cut off the local background. The program can guess in here what the background is. Okay? The ImageJ, those kind of local background subtraction has a many algorithms. I think that keep going out, probably a few of them every week, getting from the computer science people, getting. But ImageJ applies a very classic one. It's called a rolling ball subtraction. You will find the rolling ball background subtraction in the process subtract background. This is one of the functions you're going to use a lot, I assume. You click on this. So it gives you quite some of the selections, but generally I don't use most of this. Generally it's only here, the rolling ball radius in pixel unit. So let's say if I use the 50, I don't change it. I just click preview. You will see immediately that the left side the background is cut. Okay? So let's do the same thing. I draw a line. This time we'll draw most of the background one. And I do a profile. I can see the background goes down from 80 to 20. Okay? Now I'm going to do is I do the background subtraction, the rolling ball. I keep this one the 50. Now I don't change. The default is 50. And then I use the same one. I draw it the profile. So you will see now the background keep at about like 20. It's still a very noisy image. We need to do some smoothing filters here. Okay? But you will see that the same line, before we can see a clear slope that has a different background level, but now it's more uniform. And the only parameter you are using for the, let's reopen this one. So maybe I use this. Maybe let's go back to the file notepad table. Basically, the only parameter you're going to use for the subtract background is the rolling ball radius. How to choose this radius is very subjective. Okay? Now let's say if I go to 20, I would say it's about the same. Okay? You can try more. I go to 10. Now it seems like too small. Now if I go to 5, now it began to say, it actually began to cut the background inside the cell. They consider the cell has certain sides that the intensity kind of a smooth inside the cell. They will consider that part is also a background. It began to cut. So generally, that's what kind of size you put in here. I normally try to put it a little bit larger. And the rule on this is you go through here, you try to find what is the maximum size. Probably like I will say, this cell is pretty big. Then I draw a diameter of this cell. I will say something like this. I draw. And then I measure it. So this diameter is about 16 pixels. Here our unit is in pixel. I go to image property. No. Sorry. Let's change it to pixel. Just easy to work. Now I measure it. So now the diameter is about 51 pixels. Okay. So I will choose the radius starting point about the largest diameter of the object inside your image. The rolling ball works very well with if your object is a round shape like cell and there are spots in your field of view. So they're going around, the majority of the field of view is still the background. It works best in this kind of image. In other images, it may not work the best. But if you have the cell, it's kind of sparse in the field of view that you can use the rolling ball subtract background. And this one, I would suggest the starting point is you find the biggest cell, you measure the diameter in pixel units, and then you use that one to starting here. And then you can play around with this number to say what result give you the best. What value gives you the best the result. The value choose is quite subjective, but again, what we want to do is once you set here like a 50, you keep 50 for all your images. All your images comes here has to do a subtract background first. Okay? But again, as I mentioned, this is not actually a very good way to do it. In this case, you have to go back. The best way to do it is to go back to your microscope, fix this problem, then you don't have this. Yeah. So let's say if we go to the other one, the background image. So this is basically the same one we used for the previous result, but it's not only noisy, but also the right side is much stronger than the left side. So if you directly use the threshold holding, you will say once you set a good cell mask on the right side, then the left side we basically lost the cell. If you have a good cell collection on the left side, then the right side is all the mask. Okay? So for this one, what I'll do is I come into here. Let's say I draw a line. This is my line. Then I measure it. So this length is about 12. Let's make sure this should be the pixel unit. Yeah. So 12. So what I will say is I will about 12. I will go to the rolling ball, subtract background. Let's try the 15. So I make the background smooth. I do another filter. This time I use a Gaussian blur with radius 1. Apply it. Then I go to the something like this. I think this is good. Or you can use the different algorithm. This is the OTFU. Let's try Lee. Oh, this time I think maybe the Lee method is good. I apply it. Same thing, once you get a mask image, fill the hole, watershed, then analyze particle. Same has to be bigger, at least bigger than 10 micron, exclude anything on the edge. And now let's go back. This is our raw image. This is our selection. So I would say I'm not a very high standard guy, actually. Really. I would say it's actually pretty good. Consider our incoming data is actually not very good data. And all we did is we did a background subtraction. We corrected that the background on the right side is higher on the left side. And then we do a Gaussian blur smoothing. We correct the problem that our image is noisy. And then we directly go to the thresholding. I use the algorithm D and apply the mask, apply the thresholding and get the mask image to the standard, fill the hole, the water shading, cut out the connecting, those objects, and then go to analyze particles. And I will say based on this image, we get a pretty nice the outline, the ROI for the cells. The intensity measurement may have some problem because we know the right side is higher than the left side. Actually, probably not coming from the sample. It's from the uneven illumination. But the cell size, I would say, much better kind of a reliable result. We can compare with the different conditions. So those are two things. You can basically get an image, which is not ideal to directly use the thresholding to separate them into their object and the background. Okay? And always, if you get a non-ideal image to do your image analysis, first always try to say, do I have done all I can do to on the microscope side to get the best raw image? You always ask you this. Always try to get the best image you can work with to start. That makes your life much easier, your result much reliable and consistent. I mean, ImageJ is actually a very powerful software, but it's a processing machine. Like any machine, the basic rule is garbage in, garbage out. If your incoming data is not good, no matter how powerful your software is, you cannot expect to give you very good results. If your incoming data is very bad, the software will give you very good result. You shouldn't trust it either. Getting? Your data needs to be reasonably good to give you reasonable results. Okay? So always on the imaging analysis, it's the same. It's also coupled with the image acquisition. Do not separate them. Okay? I saw the users, they spend like 2 months, 3 months on the microscope, get all the data, and then they say, okay, now I'm going to write a paper. I'm going to analyze the image. Then I realized, oh, my image is too noisy. I should use a higher magnification to get a better resolution on this. Then it's kind of too late. Some of them, as we show here, we can use the digital imaging analysis to help you to combat that. But some of them we cannot help. Your raw image does not have the resolution you need. We cannot increase this on the digital side. Okay? So always when you begin to take your picture, try to get a good picture and then you analyze it. Then once you analyze it, you realize what's wrong with my raw image. Is that too noisy? Is that pixel too big, too small? How can I improve that on the acquisition part and help me on the analysis part? Then you go back to your microscope, change the parameters, and get better image. Then you go the analysis again. By the end, you found the right protocol on the microscope side. Guarantee you'll get the best raw data you can. Then you begin to take all your images. Then you do your analysis part. That makes your life actually much easier later. Just try to spend more time at the beginning. Help you make sure you get the best raw data and you get the analysis protocol on the digital side to give you the reliable results. And I say, any questions for this, the uneven elimination side? I mean, you can unmute yourself in anytime if you want to ask any question. So we have practice this one, and you can use this one. Try to just try on yourself, getting to see how can I get the best kind of a mask image for this rise, this kind of hand draw neuron, and also the same thing as this cell we use in here. And we actually have a solution one to show this is what I will do. It's just a suggestion. You can try to set your protocol, and probably it's better than mine, at least by your thinking. It's always your data, your choice. You go through the protocols to try to find what you think is the best for your data, and you stick with this protocol. And if you're interested in the rolling ball subtraction, I actually copy the original paper of the rolling ball, the background. As you can see, this is in a journal called Computer. It's actually in 1983. The same as all the stress shielding papers, I'm pretty sure you don't want to read the paper, getting? It makes no sense to actually read it or understand how it is done. We only need to know it works for us. And then we just apply it one, use the same parameter on all the images. Then I guarantee my image has the same treatment. so the results are consistent. We can compare the results on different conditions. Okay? But then another thing is that in those computer image, the computer paper, if a paper is like a 40 years old, almost like a 40 years old, and people are still using it, and that means it is very, very good. Okay? So it is very, very good. Once you ever see more than 50% of the time you apply this one to your image, you can get a pretty nice the result. This is the function you're going to use a lot, I assume. But again, you have to try on your image to see how it works. So if no questions, we're going to go to the last part for today. That's for the image, the image calculator. That's it. You have two images. You can do the calculation between these two images. Let's say I go to the image calculator. The same thing. This is my cell image. As we can see, it's an uneven image. Okay? And we want to correct it. Okay? The best way to correct it is we go back to the microscope and change it, to realign it. Okay? Another way to do it is sometimes the system is too old. Some mirror you cannot tune it much. So if this is the best I can do to get a raw image, what we can do is we can get a reference image on how the uneven illumination is. Then we normalize to that reference image. So what we do is this is our sample. And then we have some reference slide, something you can buy very cheap, like a fluorescence slide. So basically, they make sure the fluorescence slide that it's even among all the slides. And then when you put that slide on your microscope, you will get something like this. Again, you will see left side is stronger than the right side. But here we know we're using a reference slide. The intensity should be same. So all the difference coming here must be coming from the illumination unevenness. So basically, we're going to use this one to normalize this. We'll do a divide. This one divide by this. Here is stronger, but here is also stronger. So when you divide it, this will be similar as the weaker signal divided by the weaker signal. But to divide on this is not that simple. You cannot directly divide it here. If you directly here, all the image in this both 8-bit, then all the signal become like a very small. So what I will do is I have the reference image, let's say it's 8-bit image. I will first make it I will first actually measure what is the mean intensity. I want to normalize to the mean intensity. So this reference image, the mean intensity is 62.5. So I remember that. And then I will change this one to a 32-bit image. This makes it can be has the decimal point. The intensity of each pixel can be like a 1.223, 0.74. I will make it 32. Now, if you move into here, you see the intensity value here is still like a 61 is the integer. Then I will use this one. I will make this one normalize the mean intensity to 1. So that is, I will divide all the pixels in here by this mean intensity value. That you can do by the math. If you want to do some arithmetic operation on every single pixel, I will do this one. Everything divided by 6.2.57595. You will see it become kind of a dark, but it just the intensity goes pretty low. once you show up in the contrast, it's basically the same. So now it will move around. You will see here the intensity is more like 1.5. This part is more like 0.6, getting? But the mean intensity of this whole field will be about 1. Then we can normalize this image by here. So what I will do is I will use this image, every single pixel. I pick up the intensity value, divide by the corresponding pixel intensity here. And after I do that, I will see what the result image is. So the image calculator is in the process. They call the image calculator. So we have 2 images, image 1 and 2. We have image 1 is the cell, image 2 is our reference. The operation will be divide. This 2 image has to be the same size. If it doesn't have the same size, you cannot do it. Cell, this one divide by this, I will say, give me a new image. If you do not click the create new window, it will overwrite the cell.tip, overwrite the first image. In this time, I want to get a new window. I will compare with the original cell. I will say, okay. So this is the result. So this one, let's say if I do a thresholding, as you can see, we're still kind of a noisy image. We haven't changed that. We still need to do some smoothing filter on it. But you can see when you move around it, the right side and the left side is normalized. Okay? They have the same kind of background. We kind of corrected the uneven illumination. So this is another way to achieve the correct the uneven illumination part. It's better than the rolling ball subtraction. Getting? Those are more like because we actually did measure reference image. So this we can actually rely on to compare the intensity of here to here. We have a physical kind of measure the difference. So now we can actually compare this cell here to this one. Ready? If you just using the rolling ball subtraction, you can kind of do this, but you do not have a much more confidence in that. But here you can actually, because we actually measure the reference image. So we did do the correction. We did correct it for the uneven illumination. Correct it from the lights, the excitation lights difference here and here. But this is actually much more complicated. Getting? It's not that complicated, but you do need to apply for the reference image, normalize that one to 1, that's divided by the mean intensity value, and change it to the 32-bit image. Then you can do the calculation on it. And one more thing is actually this reference image, I didn't actually measure it. You can kind of in a cheat way to get what the reference is. Okay? If you can't really measure, you do not have a fluorescence slide measure. What I get is the references. I have this image. I go to the smoothing Gaussian blur. I think I go to 100. So once those smoothing ones, you make it very high radius. You kind of really smooth it out to the whole environment. And if your cells are sparse, your background has a much bigger area than your cells. Then when you smooth it out that much, you kind of get what the background illumination is. That's sometimes you can see people intentionally to use a very large radius from the smooth filter. What they do is not to try to smooth the signal. what they want to do is actually they want to simulate the background. So now I use this one, I simulate the background, then I use this as a reference image, then I can correct this cell. It's not the best way, but it's kind of come in handy. You don't need to go back to your microscope to actually measure the reference image. But again, if this image happens, if you get an image like this, always try your best to go back to your microscope. Okay? Try to fix the problem. And then you can get an image. You do not have this problem, the uneven illumination problem. Okay? But if your image is already like this, you have to analyze this one. The ImageJ does have some the functions we can use. Here we can do some like smoothing the filters to make the image less noisy. We can use the rolling door background subtraction to make it more uniform through the whole field of view. We can also try to get the reference image and use the image calculator to correct this function. So all those functions help you to working on your raw image. And after those the process, you can go through the analyze the image, adjust thresholding to get a nice mask. All we did here is to help us to get a nice mask image. Once you get a nice mask image, you use the analyze particles. You can automatically get the ROI of your object, and then you can do all the calculation you want. Remember to apply it on the raw image after you get it. So, any questions? Okay.
I have a
Yes,
question.
please. Oh, go ahead.
I just wanted to know if you use a reference and if you further use rolling ball subtraction, is that okay in order to improve the analysis, or is reiterative?
If you already have a reference image, I will suggest you to use the reference image. Okay? So that's actually corrected the uneven illumination. This actually measure how even your illumination is. Then I correct it. Okay? That's much more reliable than the rolling ball. Rolling ball background subtraction kind of do the same thing, but it's not as good as you use the reference image.
So you should stick to one method only, right?
Yeah, you should speak with one.
Okay.
Always try
thanks.
to, if you use the rolling ball, then you always use the rolling ball. Make sure the protocol is the same. You treat all the images the same.
Thank you.
I've managed to get the reference image, but it's black. How did you add the color to the reference image?
Oh, this, you mean the color like this?
No, you're just where it had the reference image, but it was just a gradient of colors.
Like this? The color is I just ask you to show up like the image, lookup table. It's kind of what color you want to show the image. I use the file. So basically this one, the file lookup table, they show different pixel with a different color based on the intensity value. So here I can show it in the grayscale. So that's only black and white. And they have a lot of lookup tables here you can choose. It's just the way how it show your image. It doesn't affect your pixel intensity. It's just for some weak images, normally I like to use the file. That makes it much easier to see it more clearly. Like here we use the blue color. If you use the green one, it maybe looks better for the human eye. And I think I use the file, which actually has more contrast, just for showing how the image is.
Okay, thank you.
So if you have no other questions, the last few minutes, I will just show you something I will call the spy game. It just once you get to the image, the calculator, I mean, we have learned the ImageJ, we may try to do something not just for the image analysis, do something like in, assuming if later on in your life you want to think about change your career, like to be a spy, and this may, to learn the ImageJ may actually help you. Okay? So our goal is to say, like in this, I open the spy game picture. There's a picture of both. Okay? But we actually have hidden some messages inside this image. Yeah, getting? So if you just send out this image, people can check with that. You can check with the, in this case, and you can check with the thresholding, the brightness, the contrast. I don't think you can get anything about this. It looks like a simple image. Okay? But if you know you actually did something to hide some message inside this image, then you only need a simple like ImageJ. It's a free software. You can download it anywhere. So you open this image, your spy, your college send you this picture, you know it's containing some very important message. All you need to know is I go to the image, no, actually process, mask, binary end. So all you need to do is we have a 16 image. You input 80 and followed by 81. You click OK. It looks black. You just need to change the contrast. Then you will store the image, the message. This is a very classic one, how to hide one image in another image. The whole goal is that the whole point to do this is your hidden image, your secret image, only use the lower bit part of your original image. Getting? So if you want to achieve this one, to hide your own message, I can show you a simple step to do it here. So if this is our original image, you make it 16 bits. It's a 16-bit image. And this is our hidden image. These two images has to be the same size. Then we can use the image, the calculator. This one needs to be 8 bits. So the intensity is from 0 from 255. This one has to be a 16 bits, the image in the full dynamic range. Getting? So the intensity, as you can check here, is about in the 40,000 range. That's we can hide the small intensity image into here. So all you need to do is this is a 16-bit image. This is 8-bit image. Go to the 16-bit image to process, mask, binary end. In this case, you input 81 first and followed by 80. So this actually clear out the lower 8 bits for this image. But since we only clear the lower bit position, it doesn't really change the intensity value. So you look at the image, it's like the same. We actually did change something, but it's very minor. And then this is an 8-bit image. Then we can add this one into this. So I will go to process, image calculator. This is the original image. This is our area 51 image. I use the add together. I don't create a new image. I overwrite this one. Now I close it. So this is my final image. It doesn't say any different, even though we add my secret image into it, because the added image has a very low intensity value compared to those images. But it's hidden in all the lower bit depths in here. So once you have this image, you save it, you send it to your friend, your agent friend. And when he got it, he know how we did it. All he need to know is open this image, did exactly what we did at the beginning, mask, binary, and here is 80 first. Remove out the bold one and keep out the lower bit. Then just do a brightness contrast. Then you get here. Just in case, just once they, sometimes we go through the ImageJ, always we're doing on your scientific images. Sometimes you want to make it a little bit fun, make it useful, or you can keep as kind of secret kind of communication way to with your significant others, or in the future, maybe you do want to be a spy. It can be helpful. Okay? But don't do like this because everyone know how this is done. You need to figure out something more complicated, but basic principle is like this. I'm going to quit my screen share. Any questions?
So I do have a question. The Calculator Plus is got more functionality than Calculator for, and so do you usually use the plain old Calculator, or if you're doing a lot of this, you use Calculator Plus?
For my case, normally I just use the image calculator. That's, I think, is enough for me. But I mean, you can use that plus, getting, because many times that I believe that if you download Fiji, the calculator plus is already in there. Getting?
Right.
But sometimes people only download from the ImageJ, the IH. You have to go through all the plugins. So you just feel what's best fit for you. Yeah.
Okay, so there's nothing wrong with using Calculator Plus then?
No, nothing wrong. Because for my case, if I write a code for my users, I do not assume they have all the updated one. I assume they have the basic ImageJ function, so they can run. I send them the code they can run on their own computer. Getting? So I choose to use all the basic functions. Getting? But if you know you're working on your own project, you just found what is the best for you feel is more the best way and the most comfortable way to do it.
Thank you. Perfect. Perfect.
I'm using a Mac computer, and for some reason, like when I was following the steps that you were showing us for the spy game, I didn't get the like secret message.
Also, I'll just do it one more time, okay? So this is spy, okay? And I process mass binary and so 80 and 81. Then I click OK. Then I go into here. Did that work?
Let me try it right now, and I can let you know.
So eventually, as you can see, here we actually don't need 8 bits to show you the message. If you only need to show a text, you only need 1 bit. Getting? And you don't need to only use the lowest bit. You can even use the up to 8 bits, and you can use even other reference image to use which bit I use based on that picture. So in certain case, if you can do it to write a code to make it more complicated, you can even tell people this is how I do it. But if they do not have that reference picture, they can't decode it. It's like I can tell you how I code my image into it. But if you do not have the key, you do not have the reference image, I know at each pixel which bit I use to pick it up. You still cannot decode it. Yeah, get it? So it's actually quite powerful. But in that case, you do have to write your own code to select a very good reference picture to do it.
It worked. Thank you so much.
Yeah. Okay, so if no other question, I will end it here. So thanks for joining us, and we will have another tool, the make sense of the management Tuesday, and also more detail on segmentation and the thresholding on Wednesday. That's actually basically the same thing what I did last November. We actually have the recording on the website on our course, the training section, the website. So you can go through that. Will be basically the same. But if you're interested, you can also join that. Okay. So that will end today. Thanks for coming, Kelly. Bye, Kelly.
Thank you.
Thank you.